So in the public chat, I'm reposting for recording reasons. Here's the resource page that I gave you that we started working on last week, where we did this problem together and solve. And then I asked you to work on these as well as the 2.6 part 1 assignment. So from here, what I want to do is just kind of run through all 3 of these, 2 of them on slides, 1 on a Jamboard, and then answer a couple questions and get you kind of set up for things kind of going forward. So that's the general plan for today. So I want to go with the hypothetical square. So it grows so that the length of its sides are increasing at a rate of 8 meters a minute. How fast is the area of the square changing when the sides are 5 meters each? So when I'm hearing that, there's a couple different things I hear. I hear sides lengths and I hear area. So I should try to get an equation that has side lengths and area in it so I can work from there. So area equals side squared. Now I need to get a rate. In order to get rates, I need derivatives. So let's take the derivative of both sides with respect to t. Again, d over dt is a verb, where it says we're going to take the derivative of whatever's in brackets with respect to whatever variables down below. And if they're different variables, we're assuming that a is a composite function, that a is somehow a function of time. We don't know how, but we know it is. Same thing with s. And again, it's a composite function, so we have to remember to use chain rule and multiply by whatever the derivative of a or s is. We usually don't know that. So, all right, here we go. Well, the derivative of a is 1, but because it's by chain rule, it's a composed function. It's 1 times dA dt, or just dA over dt. Derivative of s squared is just 2s. But again, because we're assuming it's a composite function, it's 2s times ds dt, the derivative of whatever s is. At this point, we can start plugging in things we know. We have the side lengths are increasing at a rate of 8 meters a minute, which means ds dt is positive 8. And we know the sides are 5 meters each. So we can plug those in. It's pretty straightforward on this one. Boomtown. There's that. Question I want you to think about, and then you can, I just want you to kind of mull this over and think for a little bit. So coming back to this one, here we have a relationship between dA dt and ds dt. As the side lengths get bigger, does dA dt keep increasing? Does it stop and start decreasing? Because we know ds dt is constant, but is dA dt constant? It's positive. Is it going to get more positive, less positive? Is it going to change over time? And you can after you think about it, verify by plugging in a couple different side lengths. I'm actively not going to answer that question right away. I want you to just kind of think about it and let it sit and stew, because sometimes that's even better than answering it right away, because I want you to think and think. And the more perturbed you get, then I can come back and whatever I say will have a little more impact. All right. This one, the oil spilling from the ruptured tanker spreads in a circle on the surface of the ocean. The radius of the spill increases at a rate of 4 meters per minute. How fast is the area of the spill increasing when the radius is 11 meters? I see radius and I see area, and I heard the word circle. So probably I need the area of a circle. And I'm dealing with rates, so I need to take a derivative. Bam. And from there, well, let's do the derivative of both sides. The derivative of a normally would just be 1, but because it's with respect to t, it's 1 times dA dt. And for pi r squared, pi is just a constant, so it just stays there. Normally, the derivative of pi r squared is going to be 2 pi r, or pi times 2r in this case. It's the exact same thing. I just left it the way so you keep seeing the derivative. But again, because it's with respect to time and not r, we have to multiply by dr dt. So I realized last hour, and I didn't have time to change it, that I put these out of order animation-wise, but that's fine, whatever. So we'll go over, I'll turn the pointer on. So we get dA dt equals pi times 2r dr dt. Again, normally I would probably rearrange this so it's 2 pi r, so it looks more familiar. I did it this way just so you can see, hey, look, there's 2r, r squared. That's the derivative of r squared. Yay! Times dr dt. Looking back at the information we know, we want to know how fast the area is changing when the radius is 11, and we know the radius is changing at 4 meters a minute, which that's r and dr dt. Bam, bam. There they are. Not too shabby. And then we can solve from there. Which, by the way, means that the spill is getting worse and worse over time if you look at this relationship. Because this looks like almost the exact same relationship we saw in the previous problem. So as the radius gets bigger, the area is increasing at a faster and faster rate because the radius is increasing at a constant rate, which means the area is going to get bigger and bigger and bigger. All right. We are going to go to Jamboard and do this problem. Oh, did I put that back? I did. You know what? I'm just going to do it like this. Yeah. Utility guy is here. Oh, for... Yeah, he just rang the door. Okay. Oh, the utility guy's here. That sucks. All right. So I'm going to change how I'm doing this. Slide 1 is the setup, and slide 2 is kind of open. I need to go talk to a guy real quick. I apologize. Look at slide 3, see if you can interpret that, and then I'll come back and I'll curate it and redo it on slide 1. I apologize. Sorry about that, folks. There's a utility guy that came and had didn't know they were coming today. Sorry. I really, really apologize. That sucks, but you know what? The good thing about everything is that we're all just kind of working things out together. All right. So if you had the opportunity to look at slide 3, um, the place where we're going to start is by writing the equation for volume. So let's see, volume equals side length cubed. All right, since the side length cubed, we have everything we need there. So now let's take the derivative of both sides. So we get d over dt of v equals, sorry for my handwriting, I couldn't get my stylus out and I'm using a different stylus. So from this, left-hand side, I'll get derivative of volume would be 1 times dv dt. So I'm just going to write equals, let's see, the derivative of s cubed to be 3s squared, and then times ds dt. So from there, we want to start plugging things in. So I have volume. Oh, thought I changed that. So I have volume when the volume's 125 meters cubed. And I also have the rate the volume's changing at 4 meters a minute cubed. So there's the rate the volume's changing. But as I'm looking at this equation, on the right-hand side, I don't see volume there. That's an issue. If you spend some time looking at the other slide, something to note is right up here, this first equation. We can solve for we can use the volume to figure out the side length because that's what we have down there. So switch back to the pen. So I can say 125 equals s cubed, which means by cube rooting, s equals 5. So we can take that information and plug it in right there. And then ds dt is the thing that we already know, or we don't know when we're trying to solve for that. So as we plug things in, I get 4 equals 3 times 5 squared ds dt, which 3 times 5 squared is 75. So I can say 4 over 75 meters a minute equals ds dt. Boomtown. And that's how this one works. So there's a couple different things about this one, that in the sense that you had to use that initial equation to solve for the variable you actually needed. Another way that I've seen people do this one is solve the initial equation for s, and then just work with the cube root of v, which totally works and also will get you the exact same thing. And then you just don't have to plug things back into that v equals s cubed equation. So that's kind of a fun fact there. All right. Here's the last thing I wanted to do is keep reminding you, have you drawn a picture? For the first couple problems, for most of the assignment of part 1, there aren't tons of pictures to draw. So you might struggle with that a little bit. And so don't worry about it so much. But whenever there's even a little bit of context, draw a picture. Draw a picture to help you out. Now, I didn't redraw pictures because I already had something, but you should always redraw the picture. So you can label it and kind of go from there. And maybe I should model that better. Not just say, well, I didn't do it, but you should. That's kind of a silly thing to say. But anyways, have you drawn a picture? You should. If you haven't, draw one, label it, make sure you've defined what each variable represents. That's it, except for some tips. So as again, part 2 assignment is 5 problems. They're all kind of contextual problems. I have some tips for each of them. The one that I really want to point out is I want to draw a picture for 29 for you. And the reason I want to draw a picture for you for 29, I want to draw a picture for 29 so that because the picture in the book's just weird. Let's take that. All right. So in the book, it's talking about 2 planes. Here's a plane. That's exactly what a plane looks like. Here's a different plane. I've been on planes before. I know what they look like. They look exactly like that. So now I'm going to draw a right triangle. My recommendation for going about this one is label this length A, this length B, and this length C. I do that intentionally to kind of lead you about how can you relate all 3 of those things at the same time. You could get rid of C by replacing it with square root of A squared plus B squared, but I think that'll make your life way harder. So I just leave it like this. A thing to note once you have this diagram is that when you get working on your equation, dA over dt and dB over dt are negative. Okay. Those are the big things I need you to know there. Those tips will help as you read and think about those problems. And that is what I actually have for you. That's well placed, period, by the way. So at this point, I got about 5 minutes left. So what I was hoping was, I'll send that in a moment. What questions do you have about anything like calculus, math, school, life? What questions do you have? You can private message or put them in the public chat. I figure at this point, I just take whatever questions you have. Oh, I thought of something else I wanted to say. I made an intentional point to say this to all my pre-calc classes, but I want to make sure I say it to you all too. Thank you. Thank you for kind of keep working with me and doing the best you can through this time. It's not an easy time for any of us going through it. Like everyone you know is going through trauma right now. Some people are acknowledging it and some people aren't. And those that aren't are going to be dealing with the problems for much longer than those of us that are. So it's a hard time. It's hard for everyone you know. Some people are, again, just kind of faking their way through it a little more and maybe look like they're doing just fine. Maybe not. Like today, my mental health, I'm doing pretty well today. Today's going pretty well. We'll see how I am after 2 days of conferences. We'll see how I am after 2 days of conferences. But generally, I'm doing fine. Just kind of ebbs and flows. Like the hardest thing for me right now is trying to figure out like what's a healthy intersection of work time for me. Like where does what I expect of myself, what you expect of me, what my higher ups expect of me, what your parents expect of me, what the community expects of me, trying to find what my family expects of me. I keep forgetting about that too. Like trying to find the intersection of all that and what's the healthy thing. Because I can't do all of those. I don't have enough of me or enough time to satisfy all, I think, 6 of those. So I'm trying to figure out how I can do the best I can during that time. And some days I completely ignore like 3 of them. Because it's just like I just can't. I just can't today. So I just need to let you know that I appreciate that when you're here and engaging with stuff and trying things. I really appreciate you being here and doing that. Like for even just logging in to class every day can just be a struggle depending on where your mental health's at. And I want to acknowledge that and say thank you for being able to log in and just be here. Yeah. I don't know. I think it's important to know that everything is not fine. Everything's not okay. Like this is not how anything's supposed to be. And like we could get going on what's going on with COVID in Wisconsin about how everything with Wisconsin, but I'm going to try not to talk about it right now because I'm not sure it's going to benefit any of us at this point. And I don't know. There's more things we could do, but I'm not going to get into that. I would love to, but I don't. I'm just going to move on. Anyways, I'm hoping that I get to see y'all face to face for even like a day this year. Hoping that I'll get to see you fourth quarter. But I don't think I'm going to see you before fourth quarter. And I'm going to be optimistic and say that I'll see you fourth quarter. And that's something I'm struggling with too, because it sucks. Like, at least with all y'all in Kelk, like I had you last year. So like I know you and I know what you look like and I kind of know some like extra things about you and stuff. But like I'm thinking about my pre-Cal kids. Like I got 100 of them and I know a couple of them from previous years. A lot of them I have no idea who they are. And some of them have never turned on their camera. So I literally don't know what they look like. Except for like when I take attendance in Infinite Campus, but that ain't the same thing. And a lot of and that's from a picture from last year. So a lot of you have changed in a year, especially juniors, seniors, or sophomores, like sophomore to junior. There's a big transition there. I'm just kind of talking and ranting right now and just kind of getting things off my chest. So, yeah. Oh, and part of where I was going to go with that is I'm hoping to try to have like let you know at the beginning of the week what to expect more for the rest of the week. I have a lot of self-doubt as I'm planning things for Kelk right now. So my plans for the day or for the week kind of change day to day, sometimes hour by hour, minute to minute. And I just have a lot of self-doubt about everything. And I'm trying to just keep doing the best I can about it. Yeah. I'm also, by the way, going on to a different topic. I'll work on trying to get some more of your grades up to date and assessing what you have in Schoology. So thanks for submitting things. If you have stuff you haven't submitted, please remember to do that. I'm going to try to start getting those in there and giving you some reminders so that before parent-teacher conferences that it's a little more up to date than it currently is. Well, if you don't have any other questions or anything, have a great day, folks. Thanks for bearing with me through everything, and I appreciate everything you do as you're here, and have a wonderful day.